All right, I've got about a minute past the hour. Let's get started. Thanks everybody for jumping on. This is a fun session. And today I'm going to be highlighting a model that was provided to us by one of our partners, Cobra Aero. You can see the engine right here. You probably saw the pictures in the promotion, but here's the engine that they provided for us. Let me go over to their website and just give them a shout out. So Cobra Aero is making engines, amongst other things, in the UAV market, and you can see one of those actually being printed right there. Let's see. I think they have, yeah, if you look under the capability sections, you can see some of the iterations of what these small engines look like. They were previously cast with fins on the outside of engines, as engines have been manufactured for quite some time. Now they've turned to some advanced manufacturing techniques, additive, and have gotten a little bit, have really been able to take some simulation data to drive the characteristics of that lattice and optimize the design. So this is a look at one of the, this image is pre additive manufactured. You still have the fin design in there, but this is the engine around which they're putting this, or this is the entire engine around which they're putting that engine block. Okay. So this model will be available for you in nTop platform. So if you guys want to check this out and do your own thing with it, feel free to. All right, so what are we talking about today? Well, optimizing an engine block using nTop platform. I've set up this model to kind of work in a linear fashion, as we oftentimes do, and I've got steps under here. And I've already done most of this, but I'll go through some of these with you. And the first couple are just defining the outer frame, which you see in blue, and then the rose color is the area in which the conformal lattice is going to go. So step 2, I'm going to ignore for now because that's going to come a little bit later when I show how this is actually a repeatable workflow, but this is just more of a intermittent step if needed, but we'll need it later. Next step, step 3, is defining the simulation data. Now, what I've assumed on this model is that the simulation data is going to come from an external source. You could run most of these simulations that I have here in nTop, but I think it's a little more telling of how our customers are using simulation data and realistic that they're going to bring this in from an outside source. Okay, so let's go in and actually see what the simulation data looks like. Now, this isn't real data where I ran through a full simulation. This is just something representative, and the real thing that you would see is going to look something comparable. The point I'm trying to make, if I can summarize, is don't pay attention to the numbers and actual hotspots, if you will, but just the concept of it. If you were running a simulation on the combustion, on the heat transfer of this engine block, you would see a localization or a high temperature reading around the central axis, around the central perimeter of the bore, right? And so that's effectively what I'm showing right there. That's what the simulation data looks like coming in. This is just a cross section of it, so I can really go to any spot along the z-axis, or z-axis in this case, and see what it looks like. I've set up ahead of time the parameters. Let me draw on the screen the parameters of my lattice sizing. So the maximum strut size and the minimum. The maximum is going to correspond to where I've got the highest values, which show up in red. And the minimum, of course, is going to correspond to these areas out here. So that's just how I've set this up. The lattice type, customizable, the sizing, effectively with the unit cell size and the blend radius. And I'll show you that in a moment. If you wanted to see what this model looks like without doing any kind of custom latticing work, if you just want to see a uniform conformal lattice, well, I've set up a block that's going to show that. Okay, so pretty straightforward. Any parameters I want to change, you're going to update this, but uniform sizing across the board. And that's just for sake of comparison. That was my step 6. My step 7, I have got 2 of them in here. Actually, that should just say step 7 without the A. There we go. We'll correct that. The conformal lattice, because that's what this is. It's a lattice that's conforming to the shape of the body that I have on hand. And if I go into the side view, you'll be able to see a little more what I'm talking about. This is just an overall view to show you, give you a bird's eye view of what the lattice sizing is going to look like. Obviously, in the center areas, you're seeing the thickness increasing, and everywhere else it is decreased. So let's go look at what that final part looks like, which is just the previous view with the extraneous lattices sort of stripped away. Okay, here we go. It's going to make a little more sense if I go into a cross-section view. There we go. You notice the resolution doesn't look all that great, and that's okay. I'm just sacrificing a bit of that to get you the speed so I can get you something a bit quicker on the screen. But of course, I could go down and increase this to high or highest. All right, so I've got the simulation data that has driven the lattice sizing, and around the center board, that's where it's thicker. Okay, so that's great. Now, what happens if you have, not if, but when you have a secondary simulation data that's maybe you need a different type of study done? This was a thermal on the combustion. What if you want to strength? What if you want to characterize the strength around this? And you want to have that feed the lattice sizing. Well, so I've done that with separate data. Let's open up engine stress, and I'll turn this off for a moment, and we'll go look at what the simulation data looks like. Again, this is representative. This isn't actual data, so please don't pick this apart and say, well, of course this isn't real. The stresses wouldn't look like that, but this is representative. This is where you're going to see a stress concentration along the outside based on maybe external forces acting on this, right? And it's going to vary to some degree or another. All right, so that's what that looks like. We'll go look at the conformal lattice, so how this takes shape. You'll notice right away that the lattice sizing conforms to the outside frame, and you get to see some sort of representation of the frame via the lattices themselves. All right, so let's go look at the final. And just a note, as I'm doing this, keep in mind, this is all real time. I mean, I've set this workflow up in advance, but I'm running all this real time. It's extremely fast. Around the perimeter, that's where you are seeing the strut size increase dramatically. Now, this might be a decent time to show off what this blend radius does. Let's drop that to 0, and you'll see wherever the struts start to intersect the body, you have no more radius. Now, this is where if I went to a higher resolution, you would see something that looks a bit more realistic. Let me just do a couple of undos and redos. Okay, here we go. So you can see kind of a larger radius where the struts meet the perimeter around there. Now it's a bit smaller, and I realize it's confusing if I'm going from cross-section to full view, but you really don't see as much of a radius. You see a little bit, and that's just the rendering issue. But if I go back to 2, yeah, it's a bit bigger over there. All right, so that's a second simulation I ran. We've done something thermal, or I've included in here. We've done something thermal. I've done stress. I wanted to simulate or take in what might represent flow data. All right, let's see what that looks like if I go into the cross-section of it. And so this is probably mimicking velocity running through here. So as airflow is going from the right to the left, the velocity is going to decrease down. Again, this is just representative. Your actual data is going to look very different, but the concept is still there. And regardless of what the new contours would actually look like, it's going to be, this is representative. So we'll take a look at the conformal lattice. And in this one, you should be able to see right away. Yeah, everything on the right is thicker. Everything on the left is thinner. Now, where I've got the velocity coming through a lot faster, maybe the desire is to have struts that are thinner, and then maybe I want thicker struts elsewhere. This is just a simple game of flip these two numbers around, the minimum and maximum. I've got them labeled as such because I want the red zones to correspond with the maximum strut size, but I would just flip these two numbers around and get the same thing. All right, so let's just look at this. And just to kind of prove it out, there we go in cross-section mode. All right, so one of the questions you're probably asking is, well, John, of course, we wouldn't, maybe we'd run these simulations separately, but at the end of the day, we're going to need to combine this data together and actually have somewhat of a multiphysics simulation, or that multiphysics data kind of fed in here. Well, all the simulation data that I have is been derived from these fields. I have created fields from the sim data. So what have I done right here? Well, I'm going to separate these two out. Okay, so let's go back in and say thermal stress. Let's open that one up. And these two are identical at the moment. I just made a copy. Call that one thermal. Let's go into this other one. And instead of this one being the thermal, I want it to be the stress. And so we'll just call this outer stress. So I have two distinct simulations. I'm not going to change the color for a moment. I just want you to see that those are in fact different. How could I integrate those two together? Well, what do you do with fields? You can do anything you want with them. In this case, I'm going to add them together, which is just the merging of these two, right? So if I look at the data now, and by the way, these have been normalized. So of course, you know, the units are completely different, but what I have mapped the highest stress value with the highest temperature and said that those both have the same values. So I've mapped them together and they line up nicely. And the same with the smallest values too. Okay, drag that into my block. This whole thing is just going to run through. And if I immediately go to a cross section, as soon as it's done, you're going to see struts that are thicker around the perimeter and the center and thinner everywhere else. Here we go. I think that is just a really impressive capability to be able to take that data in so fast, synthesize it, and have that drive the shape of this thing. Again, everything is modifiable because of this process I set up. If I want to say, well, there should actually be more lattices in there, the density should be greater, let's squeeze them in like sardines in a can, I can do that. Now, this doesn't stop here. Yeah, there we go. They're a lot tighter. There's one more thing I want to do. Now, let's just kind of go back to where I was before. Here we go. It's this. All right, so I've effectively done an undo to get back to that original position where this variable I have set up to locate the external simulation that's put in there to turn that into a field. Okay, so where am I going with this? Well, I haven't just built a part in front of you, and I haven't just incorporated simulation data, but I've built what we like to call this repeatable process, so that either the next engine or the next anything that comes along, I can use this process and build something right on top of it. So one of our favorite parts we like to show off is this impeller. Why? Well, because it's complex, it's real. This is not an easy kind of thing to work with in traditional tools, and certainly setting up a repeatable anything is generally going to be a big challenge, right? Well, this is where that second step comes in, if you remember. Let me back up. With the engine, I had a frame and then a designated region which I could do anything with. With a model like this, I don't have any of those regions. I just have a solid body, and that's it. So I'm going to need to shell this thing out and create a region. Well, embedded in this workflow, I've created that ability, right? So that's what this step 2 is. It's just saying, hey, tell me what the original body is, and I'm going to run through this whole thing. Of course, there's variables in there that I've got set up, such as what the offset thickness is, and that's uniform, the shell thickness, the wall thickness. But of course, that could be a variable too, and that could vary through space. So let's go through this workflow. I've imported the bodies. I should probably move those up a little more to keep things in line. The next step would be the simulation data. Okay, well, let's put that in. I've done this ahead of time and have some impeller stresses. Let's see what those look like. You can see some red areas, some areas of stress concentration that happen to be around the perimeter of this and not the center, and more specifically where the impellers meet the center body, if you will. All right, so that's where stresses tend to be higher in this one. Same thing as before. This is representative data, so don't read too much into the actual numbers. Read into the concept of this. Wherever that data happens to be, that's what's going to be affected. All right, so let's just, for sake of argument, keep my numbers the way they are. In fact, I'll go back to 8 because that's how I did this originally, and I know it's going to look okay. instead of this being a conformal lattice, I've chosen this to be a volume lattice because there's nothing for it to conform to. This was all just data brought in, a big blob, if you will. Now, what's happening is the struts are thickest right around where the impellers meet that body. That's what you'd expect. That's what I told it to do. Let's go and do a cross section now and see what it looks like. Here we go. Voila, repeatable process. You can see that it's not totally obvious, but definitely around that center area, or around the center axis, everything is a bit smaller. But as you start getting out here, the size of those lattices starts to increase quite a bit. Maybe if I go into a cross section up here, it's more noticeable. Yeah, that looks a little bit better. And it's sort of morphing into the walls. And part of the reason that it's not that apparent is probably because I have this blend radius at 2. If I drop that down, then you wouldn't see the blending quite as well. And you would see lattices a bit more distinct around that perimeter. So anyways, that's what I want to show you guys today. I'm going to end it there. If you have questions, please type them in. But just to recap, this was a workflow, a repeatable workflow for optimizing, the shape of lattices and the size of things inside of a UAV engine. But really, this could be anything. This could be any model that you want. So we'll provide this video and this file for you on our website. Looks like maybe I did such a good job in explaining this that there are no questions. But hey, please reach out to us. Find us if you have questions, email us, go to our website, fill out a form, social media. We'd love to hear from you. We want to work with you and show you what we can do to make things more efficient and help you capitalize in advanced manufacturing and design next generation parts. So I'm going to end it there. Thanks, everybody. Thanks again for watching, and have a great rest of your day.